Hello everyone. So today in this particular video we will be going through the TensorFlow binary classification. So binary classification is nothing but we'll be dividing or making our model train on two different classes. In this particular data set we will be referring to two images, okay, and our model is going to predict whether what is the type of one image versus another, right? So as you can see, I have imported all the libraries over here, and I'm just going to import it. Okay, now so if you see here, I have already imported to reduce the time, and we are using Google Colab with the TPU, so it should be pretty fast. So we are using TensorFlow 2.6.0 version, and for our visualization and debugging purposes we'll be using TensorBoard using the callback method, right? So in this one we are just created a simple function which will automatically create a directory, and all the files which will get stored in that will be like in this particular datetime format, and the tensor board will have these parameters, so it will be storing all these images and embeddings and histograms and all these things. So it is a pretty configurable configuration. So we can just skip this and we can start with the dataset part. So here, if you see here, I am taking up the ZTMTF course, Food Vision Pizza Steak .zip file. So this particular link is available on online, and we can download it. So I've downloaded it and I've unzipped it. So if you see here, I'm just run it again. So basically in the pizza stick folder there is train folder, then there is stick folder, right, in which a lot of images are there, right? So if I just remove it and if I go with the pizza folder, uh, you can see we have quite a few number of images over here, right? And just to give a summary of it, we have around 250 files which is present for the test dataset in pizza, and 250 files for the steak as well, and 750 files for the pizza in the training dataset, and the steak files are also 750, right? For the classes, I am just iterating over the pizza steak dataset, and the two folders which are there, which is the pizza and the steak. So I am just capturing them as a classes, and the class name variable I'm using for that. This is just I'm removing some .tsstore, class name which gets here, and I'm just removing it. It's just something we will ignore, right? Okay, now just to have some visualization, basically this image we are trying to visualize from the pizza folder path, and if you see here there is 512 512 3. So this is the shape of the image itself, right? uh, the width, height, and the channels. So this is what the shape means. So 512 is the width, height is 512, and 3 is the number of channels, and the channels are red, green, and blue, right? So that's a basic idea of what is the image shape and what are the number of channels in this, right? The pixels. um, okay, let's start by resizing the image itself. So in the first model that we are trying to train, we have resized the image and tried to minimize the pixels by dividing it into 255 and trying to rescale it with this particular function called as image data generator. So we have normalized it between 0 and 1 value, right? So this is a very standard way of how we can rescale our images. We have done it for both the training dataset and the test dataset, right? So here if you see, there is this flow from directory where we are passing the train directory, and all the images in that will be captured in this train data variable with the batch size of 32, target size of 2 to 4, 2 to 4, which is the width and the height, and the class mode is binary, right? So we will be using the input shape for our model as 2 to 4 comma 2 to 4 comma 3, 3 being the number of channels and 2 to 4 will be the width and the height, right? So this is just the training data set and the test data set that we are capturing over here, and we are passing that. Now for the main part, we are starting with our sequential function, and we are going with each of these layers, con 2D, convolution 2D, and max pooling, which is just the pooling part, we are flattening it. We are using the dense function as well with the ReLU mathematical operation. So yeah, we are just first layer is just making sure that we have this input size, and then we have added a few layers on top of that and try to optimize the data set that we are having, right? So yeah, it's just a basic TensorFlow model that we come up with, and we are going with the padding also, so that there is no image which has a different dimension that we want, or there is no uh, issues with the padding part, right? There is pooling also that we have done. Pooling does not affect the number of parameters, right? What is the initial and the output? So we are just doing pooling for that, right? Binary cross entropy, because this is a binary classification that we have. The optimizer is Adam that we are using, and the matrix which we want is the accuracy. So now I've already run this function. So basically in the callbacks method, this sensor board callback is there, so this log1 folder will be there. So if you see just the folder structure, if you see here, there is log1, and if I open it, there is a folder with the timestamp, and it has all the relevant files that we have while training the dataset. We'll visualize it with the TensorFlow, but this is just a 5 epoch based start over here, right? So if you see here, we got around 81 accuracy, which is pretty good. This is not using neural networks as such, or we are just doing very basic operations over here. And if you see the summary, even the number of total trainable parameters that we have is 31,000, which is quite less, right? Now coming to model number two, what we have done is we have taken 4 to 5 different layers. For each layer, we have defined the number of neurons, and it is 100 for each, and we have the activation function as real, and we have just flattened the image in the starting so that you don't have any issues with the data, and we have started with the compilation part in the second part. So this is all the same part, but if you see here, the accuracy is quite okay, 76%, but the number of parameters has increased like exponentially. It's quite high, right, compared to the original one, right? So if you see the summary part of it, the number of parameters are there in the starting, which is like the highest one, and then it decreases, right? So it's just a rough idea of how neural networks work and why we need a lot of neurons for training a particular model, right? For the visualization, we are just creating this graph and plotting the loss part for it. And if you see here, it's going drastically down, and it's again increasing up. So what I prefer is like we use tensor board for it, because it will give you per epoch wise loss that is getting for the model, and I think that's a bit more easy to use. It's dynamic in nature, and it's a bit better, I guess. So we'll go through that. Okay, now we'll go through the data augmentation part. Now we know our accuracy is not the best, but we will try to augment the data. What does data augmentation mean? So let's say if you have an image, right, of a pizza, right, and you end up like rotating it by a certain degree, or you're trying to shift the zoom range for it, right, or you try to rescale it, you try to flip it, right, you try all these combinations where you have the image and you twist and change it according to how you wish from different angles, right, in a movie theater or something. If you could imagine, right, you go from different angles and take the photo of it, right, that way. So we try to augment the data, and we create different augmented images with different parameters like rotation, zoom range, and other stuff. And this is very helpful for the model to have more better accuracy and more better data set to understand what a particular image might look like, right, which will be helpful when predicting, right? Okay, now let's just go over this comparing augmented and original image. So I've just taken an original image over here. Now if you see the augmented image over here, it is quite different, right? It's the same image which we have over here in the original, but it's slightly taken up from a different angle, right? So this is a pretty basic form of how we can augment an image, and this will be helpful for us later on when we try to create a model where these augmented images are also useful for the neural network to understand what type of class a particular image can have, right? So here in this one, just to save some time, I have created this model, and I have this is similar to the model number 2 that we have, right? And if you see here, we are reaching around 80%, so around like 76 to 80%, like 4% kind of increase that we have, right, for the neural network specifically. Right, so this is quite good. It means that our neural network is actually able to understand things in a much better way. And even this is like just for 5 epochs. If we try to increase it and we try to experiment with the number of epochs, we will see a much better result for it, and we can surely definitely try that out, right? Okay, again we have the loss curve over here. If you see here, it's going down, it's going up, it's going more down, right? Only thing we don't want is we don't want overfitting to happen to our model, right? We don't want it to be so generalized that even for our test data set it is able to identify everything correctly, right? So that is not something that we want. Otherwise it will try to generalize everything, right? Okay, now just let's try to use this tensor board for one. It's taking some time. Okay, here we go. So if you see here, now this is from log 3, which is our model 3. And if you see here, this particular epoch accuracy, right? For let's say only 5 epochs, right? It is giving me a much better idea of how the accuracy is going, right? And at each value how it is working out, right? So this is very useful information. Even you can do it with different libraries, but tensor board provides you this facility where in one shot you can do everything, right? So this is quite useful when you are trying to evaluate a model. It has even a profile plugin, which we can talk about sometime later, that gives you the fair amount of idea how much resources are getting allocated for this model to train, and how much uh, is the bandwidth for it, and how is the data getting trained for per epoch, right? So if you see here, there's a lot of information over here. Even the iterations, how much iteration it is taking, the accuracy for each iteration, and the loss part, right? And we have different images options, so you can even see if there are any images that are getting trained from the original input to the output. And I'm just going back just to see if there's anything we could. Yeah, this graph option is also there, so you can see in particular, let's say if you have what are the like steps, particularly how the model is getting trained, and where Adam optimizer is getting called, where sequential 2 is getting called layer by layer, and other stuff, right? So this is quite useful. I think we can explore this further, but for now I think this will help us a lot in terms of uh, how well we can evaluate a model and what went wrong at what particular step, right? Okay, so let's just go down. Okay, now if we see, so I got this image from Pixabay, and I just read this image. This is the original image of a pizza, right? And we check the image shape for it. Now if you see, this is 960, 120, 1280, and 3, right? So this is not going to help us because our model is trained on 224, 224, 3, right? So if you see here, we have to reshape the image and train the data, right? So one more caveat over here is the batch size, right? The batch size is somewhat a parameter that we want to have in the starting of the shape itself, right? And then you have 2 to 4 width, height, and the channels, right? So using this function, I have resized the image, and you can just go through the TensorFlow functions that are getting called here, and the shape, right? So I'm just calling it over here in this part, resize image, and this is just reading the file, decoding it, resizing it, and normalizing it, right? These are the 4 steps that it is doing, and this last part is the batch size part, so that we don't have we have like this kind of shape of it, right? Batch size 2 to 4, 1, 3. And if you see here, this is what is correct: 1 2 to 4, 2 to 4, 3, right? So we are good over here, and if you see, it has converted into a numpy array, which is useful for the machine to understand, right? Okay, now we have this model 2 dot predict, so where we are predicting the image itself and seeing whether it is correctly predicting the image, or is it there something is wrong, right? So this is giving 0.94, and when I pass this simple function for it, it's giving me the accurate pizza output, right? What is the correct one, right? What is the class for it, right? So I think, yeah, this is a rough overview how our model is doing. Now for the saving and loading part of it, you can save the model in the H5 format using this model1.save, and you can create your own model. And there is another way which TensorFlow provides, using which it creates this folder, and you can go and inside the folder and it saves different checkpoints for it, right? So these are two ways in which you can save a model. For loading a model, you can just load the model using this particular function, and you can summarize it as well, right? So yeah, this is a small notebook which I thought might be interesting for a lot of the binary classification that we want to achieve. And I think, yeah, I'll just wrap up this video for here now. The accuracy won't be the main factor which I wanted to showcase here. The idea was how binary classification works and how you can also create your own binary classification part for it, right? So, okay, so I'll see you in the next video. I hope you like this short demo, and yeah, thank you.